Hello, thanks for listening in. It's great to have you with us. The purpose of this video is to show you how to derive the quantized Dirac field Hamiltonian operator, beginning with a classical electron that radiates its velocity fields. Here's a schematic of an electron which shines like a star and radiates a 1 over r squared momentum flux field determined by multiplying the Coulomb field by a fundamental constant surface charge density. When viewed relative to a moving frame, we would write electric and magnetic momentum flux fields given by these two formulas. Of course, what we're talking about here is a flagrant violation of the principle of energy conservation. Moreover, the absence of a Coulomb field means that the electromagnetic force can only be transmitted by transverse polarized photons radiating from the acceleration fields, which are not being discussed here. Even without knowing much about the field of this particle, we can guess the classical Hamiltonian. The top formula is the particle's energy-momentum 4-vector, but a contraction with the 4 velocity determines the invariant particle Hamiltonian, shown by the floating red arrow. The step function on the right side of this formula indicates that at time tau equals 0, an electron of mass energy mc squared is created, and at proper time tau has radiated an amount of field energy proportional to that time. To justify the minus sign associated with the radiated energy, let's quantize this classical particle. We do this by dividing the Hamiltonian of the particle by the energy of an emitted quantum, and then form the complex exponential. This complex exponential will have required properties of a Dirac oscillator if the invariant energy of a radiated quantum is about 140 MeV. The number of particles radiated per second is exactly the Dirac frequency. Now let's take our theory one step further. This formula is the Hamiltonian for a radiating electron created at time tau equals 0 and then destroyed at a later time tau naught, is indicated by the presence of both creation and annihilation step functions on the right side of the formula. This simple illustration shows that the non-zero fields, shown in blue, exist within two expanding light spheres, which are in general not concentric if the particle is moving. We can expand our theory of the radiating electron to include the antiparticle. In this case, each short-lived particle will be associated with its own invariant particle Hamiltonian. But now we've written these two formulas with the time dependence of the causality steps suppressed while placing a dagger next to the creation step operator. This system of particles is starting to look a lot like a classical version of the quantized Dirac field Hamiltonian operator, and one can ask how it might be derived. To answer this question, let the system evolve for the minimal classical time for which each particle radiates an amount of energy equal to its mass energy. According to our theory, this is also the time it takes for light to traverse the radius of the electron. The total energy of this system is the sum of the two, and the quantized system will follow by replacing the classical mass energy and classical number operators with their quantum mechanical counterparts. All that remains is to provide a sum over some specified number of particles, and this will complete a very impressive derivation of the quantized Dirac field Hamiltonian operator. To close, it's important to mention that nothing has been said about the fields themselves, or how classical electron theory might be rewritten to accommodate momentum flux. It's actually very easy to do, but beyond the scope of this short video. Thanks again for listening in, and have a great day.